Question 1. So to find g of 5, we pop 5 into the g function and see what output we get, and then we take that output and pop it back into the g function for a second time and see what output we get for a second time. So popping 5 into the g function, we get 15 over 2. We then pop this into the g function again and we get 40 over 9. Now part B, we've got to state the range of g. So the domain is x is greater than or equal to 5. So substituting 5 into the function, we get 15 over 2. So that will be one extreme of the range. Now think about as x approaches infinity, we're going to have two lots of a very big number divided by a very big number. Really the plus 5 and the minus 3 as x approaches a large number are negligible. So 2x over x is 2. So as x approaches infinity, g of x is going to approach 2. So the range is y being greater than 2, because we never actually get to 2, so it's above 2. So y is greater than 2, but less than or equal to 15 over 2. So part C, find the inverse function of g of x. So we really need to change the subject. So start off by introducing y. Let's let y equal 2x plus 5 over x minus 3, and then we're going to follow through the algebra to make x the subject. So we multiply both sides by x minus 3, multiply out the bracket, giving us this. Then we make sure we have all the terms involving x on one side, all the terms without x on the other, which is we've got here. That then allows us to factorize on the left hand side, and then we can divide through by y minus 2, getting x being 3y plus 5 over y minus 2. Now remember, y was just something we artificially introduced, so our inverse function of g is 3x plus 5 over x minus 2. Now the domain of the inverse function is the same as the range of the original function. So the domain is still between 2 and 15 over 2, but of course we're talking about domain, so we're talking x. So x is greater than 2 and less than or equal to 15 over 2. Question 2. So for part A, we've got to find the position vector of D. Now we're told that D is such that A to B is the same as B to D. So let's start off by working out A to B. Now to get from A to B, we go from A back to the origin, and then from the origin to B. Now A to O, we're told is, well, not told, we're told the position vector of A is this. So this is actually O to A. So A to O is the reverse of this. So that's minus 2, minus 3, plus 4. And O to B is the position vector of B, which is 4, minus 2, 3. So adding these together, we get the vector A to B being 2, minus 5, 7, which is also what B to D must be, because they're equal. Now, B to D, think of that as going part B. Well, we're going to start off by working out what the vector AC is. Now, how do we get from A to C? We go A to O, then O to C. So A to O is the opposite of position vector A, so that's minus 2, minus 3, plus 4. And O to C is the position vector C, which is A, 5, minus 2. So adding these together, we get A minus 2, 2 and 2. So that's the vector AC. Now we're told that the length of this, the modulus of this, is 4. So when we Pythagoras this, we're going to get an answer of 4. So A minus 2 all squared plus 2 squared plus 2 squared equals 4 squared. So A minus 2 all squared must equal 8. Now square rooting both sides, we get A minus 2 being plus or minus root 8. So A is 2 plus or minus root 8. Now we're told 3 part A. So let's go and set m and n as being irrational numbers. So for example, root 3 and root 12. Now when we times those together, we obviously get root 36, which equals 6. And 6 so is obviously not irrational. So that counterexample disproves the statement. part B1. Now I think, well, there are a number of ways to think of this, but the way I would think of it, first of all, just think of the graph y equals the modulus of x. So y equals x once you've taken the modulus of it. So on the right hand side of the x-axis, it would just be straight up y equaling x. Then on the left hand side, y is equaling to the modulus of x. So rather than y equaling -1, it would be +1. Rather than -2, it would be +2, and so on. So if it was just y equal the modulus of x, you would have a V shape with the point being at 0, 0. Now all we're doing here is then just translating the graph up 3. We're adding 3 to the y value, so we just shift the graph up +3. So for B part 2, I think it's best just to draw a sketch first of all to gather your thoughts and also to help you with your explanation. So we've got our y equals modulus of x plus 3, this purple one from part 1 above. Now if we think of y equaling the modulus of x plus 3, so think of the graph of y equaling x plus 3 that would just be going down here, and going through 0, 3 down to -3, 0. Now once you get beyond that, when you would be, for example, popping -4 into the graph, you'd have -4 add 3, which would be -1, but we're putting +1. So this is the graph of the y equals the modulus of x plus 3, and we can see that the purple graph is either the same as the black graph or above it. So the graph of y equals the modulus of x plus 3 is either the same or above the graph of y equals the modulus of x plus 3. So for part 1. Now to show this, it's best if we just split this sequence which is being added into 2. So let's first of all take out the linear bit. So let's take out the sequence of 3 plus 5r, which is just like sort of the nth term one at GCSE, and then add on to that when we sum up from 1 to 16 of the 2 to the power of r. So let's just do these separately, then add them together. So the first one, so what are we saying here? We're saying this is where we've got, when our first term is going to be 3 plus 5 lots of 1, which is 8. Our second term, when r is 2, is going to be 3 plus 5 lots of 2, which is 13, and so on. So this is the sequence we're talking about here. Now that's obviously just an arithmetic sequence, and using the formula that's provided in the formula booklet, we've got a being the first term being 8, and then d being the common difference being 5, and we've got 16 terms worth, so n is 16, so 16 here, and 16 minus 1, 15 here. So just working that out, we get the sum of this arithmetic sequence being 7, 2, 8. Now then moving on to the second bit, this is the geometric sequence, because we're adding 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3, and so on. So again, this formula is given in the formula booklet for a geometric sequence, where the first term is a, the common ratio, the amount we're multiplying by each time, is r, so that's 2, and then again n is 16. So popping that into a calculator, we get the summation of this geometric sequence being 131,070. So add the two sequences together, we do indeed get 131,798. So for part 2, so let's gather our thoughts. So the first term, u1, is 2/3. Now what we're saying here is the next term is the previous term but 1 over the previous term. So our second term, u2, is going to be 1 over 2/3, which is 3 over 2. And then you can see the pattern evolving. So our third term, u3, is going to be 1 over 3 over 2, which is 2 over 3. So our sequence comprises 2/3 and 3 over 2, plus 2/3 and 3 over 2, and so on. Now, because we're doing 100 of these, we're going to be repeating the initial sequence of 2 50 times. So it's going to be 50 lots of these first two numbers added together. 100 of these because of the 100 here. So 50 lots of the 2 added together, which is 325 over 3. 5 part A. So from the formula booklet for Newton-Raphson, we have this formula here. So we just need to substitute into this formula. So our function is obviously what we're given here, so the 2x cubed plus x squared minus 1, each with the suffix n. And then our denominator is the numerator once we've differentiated it, so 3x squared plus 2x. So we've got a subtraction to do here, so really we're subtracting fractions, so we need to have a common denominator. So we need to take this first term here and choose to multiply top and bottom by 6x squared plus 2x. So that's what I've done here. So I'm timesing the numerator by this, and then obviously the denominator as well. So we've got the x to the n times this over this, so multiplying top and bottom by this, and then we're taking away this over this, which is this over this. So we've now got a single fraction, so we just need to follow through the algebra. So multiply out this bracket here, and then subtract this from it once you've multiplied out the bracket, gives us what we had to show. So part B, this is pretty straightforward. So we've just got to substitute the previous values into this formula. So x2 is going to be this formula here once we've substituted x1, which is 1, into it. So we're just substituting 1 into this, giving us 3/4. And then x3 is when we substitute x2 with the 3/4 back into it again. So we get 3/4 and 2/3. Right, so for part C, explain why for this question the Newton-Raphson method cannot be used with x1 equaling 0. Well, if it was 0, if you try and substitute 0 into this, you get a denominator of 0, and you obviously can't have a number divided by 0. Your calculator will give you maths error. So why is this denominator 0? Well, this denominator is 0 because the differential is 0. When is the differential 0? That's when there's a stationary point at x equaling 0. So question 5a part 1, calculate f of 2. Well, that's simple enough. We just substitute 2 into the function, giving us 0. So what does that tell us? That tells us that x minus 2 must be a factor. So if we take the function and divide it by the factor, we can then work out the quadratic factor. So here I've just done the long division. So on the back of 2 being a solution, we can say x minus 2 is a factor. Change of sign, note the change of sign, minus 2 not plus 2. Then do the long division, and we end up with minus 3x squared plus 2x minus 5. We knew we wouldn't get a remainder because x minus 2 is a factor. So what we can conclude is x minus 2 multiplied by minus 3x squared plus 2x minus 5. Now part B, we're told to use the answer to A part 2, so we can just see the similarity between this function here and our original function. We're basically replacing x with y squared. So we'd worked out in A part 2 that this was the product of the two algebraic fractions, so we can just write this out again, replacing an x with a y squared. So that gives me this. Now this here has no real solutions, this second one. How do I know that? Well, I can just do b squared minus 4ac, and I get the discriminant which is less than 0. I get minus 56, so I get no real solutions from here. So my real solutions have to come from this first algebraic factor, y squared minus 2. So my two real solutions are, by adding 2 and then square rooting, y equals plus or minus root 2. Now part C, deduce the number of real solutions in this range for this equation. So again, let's just go and compare our equation with the original function, and we can just see that x is being replaced by minus tan. So we're replacing x with minus tan. So again, let's just go back to this here and rewrite this product of factors we got from A part 2, but now replacing x with minus tan. So that gives me this here. Now again, leading on from part B, I know I've got no real solution, no solutions from the second bracket, so my solutions are going to come from this first bracket, minus tan theta minus 2 equaling 0. So that means that tan theta has to be minus 2, because minus 2 is plus 2 minus 2 is 0. So let's think about the number of the solutions for tan theta equaling minus 2 between 7 pi and 10 pi. So I've just done a quick little sketch up here to help me. So this is my tan graph. There's 7 pi, 8 pi, 9 pi, 10 pi. So how many solutions do I have between 7 pi and 10 pi? 1, 2, 3. 3 real solutions. Part 1. So let's start off by recognizing that sec x is just 1 over cos x. So we've got 4 sin x equaling 1 over cos x. Now let's just get rid of this fraction. Really, let's choose to multiply through by cos x. So I get 4 sin x cos x equaling 1. Now we're going to now use our sin a plus b formula, which is given in the formula booklet, but just having a and b being equal. So we've got our sin 2x equaling 2 sin x cos x. So bearing this in mind, our 4 sin x cos x is the same thing as 2 sin 2x. So we can replace this with 2 sin 2x equaling 1. Now divide through by 2, we get sin 2x equaling a half. Now let's let capital X equal 2x, and then just think, so a substitution there, and solve for sin x equaling a half. Now we're going to, what are we doing here? Yes, we're doing this between 0 and pi over 2, so our boundaries for capital X, we're doubling these, are between 0 and pi. So when does sin x equal half between 0 and pi? Well, we worked out our first solution being a half, being pi over 6, excuse me. So just using my calculator, I've inverse sinned a half with my calculator in radians mode to give me my first solution being pi over 6. I'm looking for all the solutions between 0 and pi. So my first solution is pi over 6. My second solution is this angle here, which is pi minus pi over 6, which is 5 pi over 6. So converting back from capital X to my little x, I'm going to divide each of these by 2. So my solutions to part 1 are pi over 12 and 5 pi over 12. part 2. Now there are a number of ways of doing this question, so if you've done it a different way, for example starting off by squaring both sides, that's fine. But the way I've done it is to rely on, is to go down the route of introducing r and alpha. So bearing in mind that sin theta minus alpha equals sin theta cos alpha minus cos theta sin alpha, just from the tables from our sin a minus b from the table booklets, I've then just chosen to multiply through by r. So that's my starting point. Now equating this through to 5 sin theta minus 5 cos alpha, I can see that so the sin theta is this bit, so my r cos alpha equates to 5, and my r sin alpha also equates to 5. So call this equation 1, call this equation 2. Dividing through it, 1 divided by 2, I'm left with on the left hand side r divided by r, which cancels, is just 1. Sin alpha over cos alpha is tan, 5 divided by 5 is 1. So I get tan alpha being 1, inverse tan both sides in degrees, I get alpha being 45. Now back to this fact here, if we choose to square the two, we're going to have r squared sin squared equals 5 squared, and r squared cos squared equals 5 squared. Add these together, we get this, and once we've factorized it, the sin squared alpha plus cos squared alpha cancels out. So it doesn't cancel out, excuse me, it equals 1. Sin squared plus cos squared equals 1. So r squared equals 50. So r equals root 50. So in short, we can rewrite this as being r, which is root 50, sin theta minus alpha, which is 45, and that equals 2. Now I'm then dividing through by root 50 to get this, and then I'm just repeating what I did earlier on, really the same process. Let's choose to let capital X equal theta minus 45. Let's adjust our range away from being 0 to 360 to being minus 45 to 315. Let's get our first value for sin x equaling 2 over root 50 using our calculator. So x equals inverse sin 2 over root 50 gives me 16.4. Now I'm looking for all the values between minus 45 and 315, so that's just going to pick up the 2. It's going to pick up 16.4 and 180, take away 16.4, which is 163.6. So those are my solutions for x. So for theta, I've got to add 45 to these, giving me 61.4 and 208.6 degrees. Question 8, part A. So we're asked to find a quadratic equation that fits this model. So we've got a negative parabola here, a sad face. So this is going to be a minus x squared graph at the end of the day, so bear that in mind. Now we know our two solutions are going to be at 0 and 40. So in our brackets we need to have x and x minus 40, because this would give us our solutions of 0 and 40 at 0 and at 40. Part B. So the ball passes over the horizontal bar of a set of rugby posts that is perpendicular to the path of the ball. The bar is 3 meters above the ground, so the height is 3. So we've just got to substitute in h being 3 into our equation. So substituting that in and multiplying through, we're just following through the algebra, rearranging, we can basically get this quadratic here. We have x squared minus 40x plus 100 equals 0. So our coefficient of x squared a is 1. Our coefficient of x b is minus 40. And our number on its own at the end, c, is 100. So popping that into a calculator using the quadratic function to solving, we get our two solutions being 20 plus 10 root 3 and 20 minus 10 root 3. Now we want the greatest distance one. Obviously we don't want the solution over here, so we want the 20 plus 10 root 3, which is 37.32 ... which is 37.3 meters to 3 sig figs. Part C, give one limitation of the model. Well, there are many limitations that are allowed, so I've just screenshot the mark scheme. So any of these would give you the 1 mark. Question 9. So I've kicked off by taking the formula from the booklet with regard to first principles, which is this. So substituting in, we're saying the differential d cos theta d theta equals, well, our function plus h is going to be cos theta plus h minus our function, which is cos theta, and all over h. So we are advised that we can use the cos A plus B formula. So just taking that from the formula booklet, I've just replaced cos theta plus h with cos theta cos h minus sin theta sin h. And then I factorised this. So I've just taken out the factors of sin theta and also the factors of cos theta. So what we can now say, as h approaches 0, we're now relying on these two other pieces here. So sin h over h approaches 1, so we're going to have it approaching minus 1 sin theta. And similarly, as h approaches 0, cos h minus 1 over h approaches 0, so this here becomes 0. So we're left with minus 1 sin theta plus 0 lots of cos theta, which of course is just minus sin theta as required. 10 part A. So we're told in this simple model the rate of decrease of the radius, so dr dt, is inversely proportional to the square of the radius. So this equals k over r squared. Now, we can write this as saying this is the integral of r squared dr, sort of effectively multiplying both sides by r squared, equaling the integral of k dt. So it's effectively multiplying through by dt. So big point, getting from here to here. So we're getting all the r's on one side, or the t's on the other, if you like. So we just integrate, that's easy enough. So a third r cubed equals kt plus c. We're then given a couple of facts to allow us to work out our two constants k and c. So when t is 0, r is 5. So substituting in, that shows us that c must be 125 over 3. And when t equals 4, r equals 3. So substituting in, we get 9 equaling 4k plus 125 over 3, so k is minus 49 over 6. So our equation, now that we know the two constants, can be rewritten as a third r cubed equaling minus 49 over 6 times t plus 125 over 3. Part B, find the time for the mint to completely dissolve. So we need to work through until the radius equals 0. So 0 equals minus 49 over 6t plus 125 over 3. So rearranging, we get t equaling 5.102 minutes, which is 5 minutes 6 seconds. I've just taken the 0.102 and multiplied it by 60. Part C, suggest a limitation of the model. Well, again, there are numerous limitations that have been allowed by the mark scheme. So I've just taken a snapshot of all the various possibilities from the mark scheme. So as long as you've got one of these, you'd have picked up your mark. 10 part A. So fairly straightforward. So multiply through by x minus 3, 1 minus 2x. So that gives us a plus 11x minus 6x squared equals a multiplied by x minus 3, 1 minus 2x, plus b 1 minus 2x, plus c x minus 3. So just so we're clear, we've multiplied throughout each of these terms by x minus 3, 1 minus 2x. So pop those all on the denominator, then bits and bobs cancel out. Now from then onwards we can just work out the various ones in turn. If we let x equal 3, then we can see this one here, this term here is 0, this term here is 0, so that allows us to work out that b equals 4. When x equals a half, that makes both this term and this term 0, allowing us to work out that c is minus 2. And then by just equating coefficients of x squared, the only x squareds I'm going to get here are a minus 6 here and a minus 2a over here, allowing me to work out that a equals 3. (11 part B). So I've rewritten the function in the partial fraction format, but have taken the x minus 3 and the 1 minus 2x upstairs, if you like, having those to the power of minus 1, and then I can then differentiate that, which gave me this, which I've then just rewritten in sort of fraction format. Now think about the first term. X minus 3 all squared is going to be positive, so we're going to have a negative divided by a positive, which will always be negative. So this term will always be negative. Moving on to this term here, 1 minus 2x all squared, again will always be 12 part A. So starting off with the right hand side, tan theta minus sin 2 theta, well sin 2 theta equals 2 sin theta cos theta, derived from the sin A plus B equation. So I can replace the sin 2 theta with 2 sin theta cos theta. Tan theta is sin theta over cos theta. The coses cancel out, leaving me with 2 sin squared theta. So that's as far as we've got so far. Let's just park that at 2 sin squared theta. Now think about the cos A plus B formula. That gives us cos A cos B minus sin A sin B. So if we let A and B equal theta, we've got cos 2 theta being cos squared theta minus sin squared theta. But cos squared theta equals 1 minus sin squared theta. So cos 2 theta equals 1 minus 2 sin squared theta. Rearranging that, we can see that 2 sin squared theta does indeed equal 1 minus cos squared theta, which is what we had to show. Part B. So hence solve this. So we're going to use what we have before, so we're going to replace the 1 minus cos 2x with tan x sin 2x. So my first line of working, I'm just acknowledging the fact that I'm building in part A. Now sec squared x equals tan squared x plus 1. You probably know that, but if you just need to derive that from first principles, it comes from sin squared x plus cos squared x equaling 1. I've done that over here. Now, if we now multiply out, question 13. Now, a lot of things to work our way through here. I'm going to start off by trying to work out the equation of the line L. Now, in order to do that, I need to know a point on it, which I know, EE, but I'm going to need to know the gradient, and I can work that out as it will be perpendicular to the gradient of the curve at that point. So step one, I'm going to need to work out the gradient of the curve at that point, so I'm going to need to be able to differentiate the curve. Now the curve is y equals x ln x, so to differentiate this I'm going to use the product rule. So u equals x and v equals ln x. So differentiating both of these, I get du dx being 1 and dv dx being 1 over x. Substituting into the product rule, I get the differential being 1 plus ln x. So at an x coordinate of e, my gradient of my curve at point E, I substitute e into the differential, so I get 1 plus ln e, which is 1 plus 1, which is 2. So the gradient of the curve at point E is 2, so the gradient of the normal of my line L is going to be, flip it over, change the sign, that's going to be minus a half. So nearly there with the first part. So to work out the equation of L, I can use the y minus y1 formula, substituting in the point EE and using the gradient minus a half, and I get to y equaling minus a half x plus 3 over 2e. Now the next thing I'm going to do, I'm going to break this shaded area down into two. So I'm going to have the bit to the left hand side of E, which I'm going to call R1, which will require me to integrate in a bit, and the bit to the right R2, which is just this triangle. Now I know this value is E, I know the height is E, I need to work out this point here. Now I can work out this point here because this is on the line L, and it is when y equals 0. Now I've just worked out the equation of L, so I can work out what the x value when y equals 0 by substituting 0 into this straight line equation, and that gives me that I can then work out that x equals 3e at this point here. So I can now work out the area of my triangle R2, half times base times height, half times base, a length of 2e, times a height of e, giving me e squared. Now the next thing I'm going to do is trying to work out the area R1, so I'm going to integrate under the curve, but between e and what? So I'm going to need to know what this value is here. So this is on the curve, but where the curve cuts the x-axis, so when y equals 0. Now the curve is y equals x ln x. When y equals 0, so it's going to be 0 equals x ln x. So ln x has to equal 0, so x equals 1. So this coordinate here is 1, 0. So I'm now going to integrate the curve x ln x between e and 1. Now to integrate the curve, so I'm going to integrate by parts, so I'm using the parts formula which is given in the formula booklet. So my u is going to be ln x because I know how to differentiate ln x, and my dv dx is going to be x, so make sure you get it this way round. So my du dx is 1 over x, and my v is what I get when I integrate x, which is half x squared. So substituting that in, following the parts formula, I get this. So I still need to integrate this bit on the right hand side, but this multiplied out is just half x. So integrating a half x, I get a quarter x squared. So this is what I need to substitute my limits of e and 1 into. So substituting e into this, I get half e squared minus a quarter e squared, and I subtract from that when I substitute 1 into this, which is when I get 0 and minus a quarter. So I'm getting a quarter e squared minus a quarter is a quarter e squared plus a quarter. So that is the area R2. So my overall area is R1 plus R2, so that's e squared added together with a quarter e squared plus a quarter, which gives me 5 over 4 e squared plus a quarter, which is in the format that the answer required. 14 part A. So find the number of mice in the population at the start of the study. Well, this is going to be when t equals 0. So substituting 0 into this, I get 900 over 3 plus 7 e to the power of 0. Well, e to the power of 0 is 1. So that's 900 over 3 plus 7. 900 over 10, which is 90. Part B. So we've got to show that the rate of growth dn dt can be represented by this. So we've got n equaling this. So really writing this on one level, taking the denominator upstairs to the power of minus 1. This is n, my starting point. So to differentiate this, so multiply by the current power, reduce the power by 1, and multiply by the differential of the bracket. Gives me this. And then I'm just rewriting this by taking this term downstairs, if you like, so, and then gathering up my terms at the front. So that gives me positive 900 times a quarter times 7e to the minus 0.25t over 3 plus 7e minus 0.25t all squared. Now, because what I'm aiming for is all in terms of n, I really need to rewrite these two bits here in terms of n. And so go back to my starting point where n equals this. Now with this 7 lots of e, this bit here that I've marked in yellow, I can rewrite this in terms of n. So, but starting off with this one. So what I've done, I've taken my n, I've multiplied by the 3 plus 7e, multiplied by the denominator, divided by n. So that is one formula. Taking away 3 from both sides, I can say that this equals this. So back to what I've got over here. So I can replace my 7e to the power of minus 0.25t with 900 over 900 over n minus 3, and I can replace this denominator here with 900 over n all squared. Now a lot of bits and pieces cancel out now, and then just sort of following through the algebra I can get to what I needed to, which was n multiplied by 300 minus n all over 1200. Now part C, the rate of growth is a maximum after t months. Find according to the model the value of t. So let's think about our dn dt being n multiplied by 300 minus n over 1200. This is a quadratic, it's a negative quadratic, so a quick sketch of this to help me gather my thoughts. It's 0 at 0 and 300. It's a symmetrical shape, so I'm going to get a maximum rate of growth halfway between 0 and 300, which is when n equals 1500. So I'm substituting n being 1500 back into the original formula for n, and that gives me this. So multiplying by the denominator, dividing through by 150, then taking away 3, dividing by 7, I can get to e minus 0.25t equaling 3/7. So if I then ln both sides and use the power rule, I get minus 0.25t equaling ln 3/7. So t equals ln 3/7 over minus 0.25, which is 3.389 months. Part D, according to the model, the maximum number of mice on the island is p, state the value of p. So let's go back to the number of mice on the island. Now, in order to maximize this, we're going to want this term in the denominator to equal 0. That's the smallest it can be, given it's e to the power of something. So we want this to be 0. So we're going to have 900 over 3, which is 300 mice.